to handle it using existing techniques. Example number 1. Find the zeros of f of x equals x squared plus 4x plus 5. Now, this is a classic polynomial that's quadratic to factor because a lot of people think they can factor it. But it doesn't factor well. This is prime over the real numbers. That is to say, if we try to factor this as the product of two binomials, x plus something times x plus something, if you guys recall the rule for that, you need to find two numbers that multiply together to give you 5, but add together to give you 4. So my options here are plus or minus 1 and plus or minus 5. And either one of those combinations is not going to generate a 4. That is to say, because this is a positive 5, these signs have to be the same. So if it is x minus 1 times x minus 5, that will give me x squared and a positive 5, but this will give me negative 6x in the middle. And that is not what I'm looking for. And if it is x plus 1 times x plus 5, that'll give me an x squared and a 5 on the end, but it'll give me plus 6x. And so you might say, well, switch some signs. All right, well, if this is x minus 1 times x plus 5, that'll give me x squared plus 4x, which is actually what I'm looking for here, but this is a negative 5. And so it fails here, and this just keeps going. All the combinations that you're going to try are not going to work out here. And this is x squared minus 4x minus 5. And now both of them are wrong. So this does not factor using real numbers. So we have to resort to violence. Remember that the quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Please make sure that you don't kind of know that for the exam. Make sure you absolutely know it verbatim. And our function was f of x is equal to x squared plus 4x plus 5. So this is negative 4 plus or minus the square root of 4 squared minus 4 times 1 times 5 all over 2 times 1, which simplifies to be negative 4 plus or minus the square root of 16 minus 20 over 2, which is negative 4 plus or minus the square root of negative 4 over 2. And it used to be at this point, we would throw our hands up in the air and say, oh, there's no real zeros. And you're right, there are no real zeros. So there's no real zeros because they're complex, and we need to be able to simplify that. So remember that the square root of 4 is 2, so the square root of negative 4 is 2i. So this will simplify to be negative 4 plus or minus 2i all over 2. Be careful how you simplify this. Break this up into two fractions. This is negative 4 over 2 plus or minus 2i over 2, which is negative 2 plus or minus I. And those are the zeros of the function. There's actually two here. X is equal to negative 2 plus I, or x is equal to negative 2 minus I. And you want to note that in this case, these occurred in conjugate pairs. So that's the a plus bi, where a is negative 2 and b is 1. And this is a minus bi, where a is negative 2 and b is 1. Let's do one more quick example like that. example 2, find the zeros of f of x equals 2x squared plus 8x plus 12 and factor the polynomial. We'll use the factor theorem here on the back end of this. But to get this started, let's see. F of x equals 0 if x equals negative b plus or minus the square root of b squared minus 4ac all over 2a, which here is equal to negative 8 plus or minus the square root of 8 squared minus 4 times 2 times 12 all over 2 times 2, which is negative 8 plus or minus the square root of 64 minus 84 all over 4, which is negative 8 plus or minus the square root of negative 20 over 4. Now again, this is not real. It will be complex, but you need to know how to simplify that. So, aside, the square root of negative 20 is the square root of negative 1 times 4 times 5, which is the square root of negative 1 times the square root of 4 times the square root of 5, which is I times 2 times the square root of 5, or 2I root 5. So, it sounds like an interstate. I was on 2I root 5. No big deal. Let's see. This is negative 8 plus or minus 2I root 5 all over 4. And if I break that up into two pieces, that's negative 8 over 4 plus or minus 2I root 5 over 4, or negative 2 plus or minus 1/2 I root 5. So there's two answers here. The zeros are x equals negative 2 plus or minus, sorry, let's not do plus or minus, plus 1/2 I root 5, and negative 2 minus 1/2 I root 5. So I do have two zeros. These again occur in conjugate pairs. This is the a plus bi, this is the a minus bi, where in this case b is a little bit more complicated. In both cases here, a is negative 2 and b is negative 1/2 times the square root of 5. Okay. Now, by the factor theorem, if x equals c is a 0, then x minus c is a factor. That's for f of x, right? So this means that f of x factors as x minus negative 2 plus 1/2 I root 5. I'm using parentheses there because I'm going to have to distribute that negative sign. And the other factor is x minus negative 2 minus 1/2 I root 5. But that's not exactly correct. So first off, if we simplify this a little bit and distribute the negative sign, we get x plus 2 minus 1/2 I root 5, and x plus 2 plus 1/2 I root 5. But if we multiply this out, and I'm not going to multiply it all the way out, but I just want you to pay attention to this. If we multiply these two factors together, what are we going to get? Well, we're going to get x squared, right? And that's going to be our only x term. But if we look back at our original polynomial, it didn't just start with x squared, it started with 2x squared. So you need to be careful. This isn't exactly how it factors. These are just the zeros. We're also off by a factor of 2. This is the lead coefficient. So watch out for that. That's a common mistake. We still needed to have a leading 2 when we're done multiplying it out. So this is actually how it factors. F of x is equal to 2. And you could have actually factored out a 2 in the very beginning. This is 2 times x squared plus 4x plus 6. So this is 2 times x plus 2 minus 1/2 I root 5 times x plus 2 plus 1/2 I root 5. And this has been factored completely over the complex numbers. So it's a little bit more advanced example. Oh my gosh.